In this module, we will be studying about the classification and nomenclature of haloalkanes and haloarenes. Part 1. A haloalkane molecule is formed when a hydrogen atom in an alkane molecule is replaced by a halogen atom. Some typical haloalkanes are illustrated here. This class of compounds is also called alkyl halides. Haloarenes are formed when a hydrogen atom in an aromatic compound, such as benzene, is replaced by a halogen atom. These compounds are also called aryl halides. Many organic compounds that contain halogens occur naturally. Both synthetic and naturally occurring halogenated organic compounds have important uses in medicine and research. Chloramphenicol is a naturally occurring substance produced by soil microorganisms. As you can see in the structural formula, it contains 2 chlorine atoms. Chloramphenicol is used as an effective drug in the treatment for typhoid fever. The thyroid gland, a butterfly-shaped gland at the base of your neck, produces the hormone thyroxine. Notice the 4 iodine atoms in the chemical formula. A lack of dietary iodine can lead to a deficiency of this hormone, which can eventually lead to goiter. Chloroquine, a synthetic compound, is used for the treatment of malaria. Halothane is used as a general anesthetic during surgery. These compounds are used in industries as solvents for relatively non-polar compounds and also as starting material for the synthesis of a variety of organic compounds. Haloalkanes and haloarenes can be classified in several ways. One way is to classify them based on the number of halogen atoms. Chloroethane, a monohaloalkane, and chlorobenzene, a monohaloarene, each containing 1 halogen atom, are shown here. Dihaloalkanes and dihaloarenes have 2 halogen atoms in their formulae. Trihaloalkanes and trihaloarenes with 3 halogen atoms are also known to exist. Based on the heptization of the carbon atom to which the halogen atom is bonded, monohalo compounds are classified as alkyl halides, allylic halides, benzylic halides, vinylic halides, and aryl halides. In alkyl, allyl, and benzyl halides, the halogen atom is attached to an sp3 hybridized carbon atom. On the other hand, in vinyl and aryl halides, the halogen atom is attached to an sp2 hybridized carbon atom. We'll start with the alkyl halides, or haloalkanes, which have the general formula Rx. R here represents an alkyl group. In these compounds, the halogen atom is bonded to an sp3 hybridized carbon atom. The homologous series of alkyl halides can be represented by a formula CnH2 n plus 1x. Based on the nature of the carbon atom to which the halogen atom is attached, The alkyl halides are further classified into primary, secondary, and tertiary. In primary alkyl halides, the halogen atom is attached to a primary carbon atom. For example, ethyl chloride is a primary alkyl halide. In secondary alkyl halides, the halogen atom is attached to a secondary carbon atom. Isopropyl chloride shown here is a secondary alkyl halide. In tertiary alkyl halides, the halogen atom is attached to a tertiary carbon atom. For example, in tertiary butyl chloride, the chlorine atom is attached to a tertiary carbon atom. You need to be able to recognize allylic carbons. Allylic carbons are carbon atoms bonded to a carbon atom that is doubly bonded to another carbon atom. As the illustration here shows, allylic carbons are one position away from a double bond. Allylic carbons are sp3 hybridized. Allylic haloalkanes have halogen atoms attached to allylic carbons. In benzylic halides, the halogen atom is bonded to a carbon atom with sp3 hybridization that is linked to an aromatic ring. In primary benzylic halides, the carbon attached to the halogen has only one carbon-carbon bond. Here are secondary and tertiary benzylic halides. In a secondary benzylic halide, the carbon attached to the halogen atom is bonded to two other carbons. In a tertiary benzylic halide, the attaching carbon is bonded to three other carbon atoms. It will be helpful in your chemistry studies if you can identify vinylic carbons or alkenyl carbons, as they are sometimes called. Vinylic carbons are sp2 hybridized and are double bonded to one carbon atom. The vinylic carbons in two different molecules are shown in the illustrations here. Vinylic halides have a halogen atom bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond. Two examples of vinylic halides are shown here. In aryl halides, the halogen atom is bonded to an sp2 hybridized carbon atom of an aromatic ring, as illustrated here. In this module, we will be studying about the classification and nomenclature of haloalkanes and haloarenes. Part 2. Learning the proper nomenclature of organic molecules is very important, and it takes a lot of practice. Many compounds have common names as well as systematic IUPAC names. The common name of alkyl chlorides can be found by giving the name of the alkyl group, followed by the halide. In the IUPAC nomenclature system, they are named as halo-substituted hydrocarbons. Let's write the IUPAC name of the given molecule. The longest continuous carbon chain has 4 carbon atoms, and hence the root word is but. Since the longest carbon chain is saturated, the primary suffix is ane. Thus, the name of the parent carbon chain is butane. We then need to identify the substituent and its location. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the substituent is attached. We see that the carbon atom with the substituent chlorine is in position 1. Thus, the name of the given compound is 1-chlorobutane. Let us find IUPAC names for these two molecules. The IUPAC name for the molecules on the left is 2-chloro-2-methylbutane. It is a tertiary haloalkane, as the chlorine is bonded to a carbon linked to 3 other carbon atoms. The IUPAC name for the molecules on the right is 3-chlorohexane. It is a secondary haloalkane. Notice that the chlorine is bonded to a carbon linked to 2 other carbon atoms. Now let us draw the formulae for the compounds as shown here. The illustration on the left gives the trans isomer of 2,3-dibromobute-2-ane. Shown here is the cis isomer of 2,3-dibromobute-2-ene. The common name for haloarenes give the name of the aryl group followed by the halide. Common names may use the prefixes ortho, meta, and para to indicate relative spacing 2, 3, or 4 carbons between the halogen atoms. In IUPAC nomenclature, haloarenes are named as substituted arenes, listing the location and type of the halogen atoms. Let's work through some practice problems together. What are the IUPAC names of these compounds? All 3 molecules are benzene derivatives. Remember, if more than one similar substituents are present, then we must give the location of each and include prefixes indicating the number present. The common and IUPAC name for molecule A is chlorobenzene. Molecule B is often called meta-dichlorobenzene. Its IUPAC name is 1,3-dichlorobenzene. The common name for molecule C is symmetrical trichlorobenzene, while its IUPAC name is 1,3,5-trichlorobenzene. Dihalogenated compounds with the same type of halogen atoms can be classified based on whether the halogen atoms are on the same or adjacent carbons. If the 2 halogen atoms are bonded to the same carbon atom, then it is called a germinal dihalide. Germinal dihalides in the common system are called alkylidene halides. In the IUPAC system, They are named 1,1-dihaloalkanes. Thus, the molecule shown here can be called ethylene chloride. Its IUPAC name is 1,1-dichloroethane. If two halogen atoms of the same type are bonded to adjacent carbon atoms, it is called a vicinal dihalide. Vicinal dihalides in the common system are sometimes named alkaline dihalides. In the IUPAC system, they are named 1,2-dihaloalkanes. For the molecule shown here, the common name is ethylene dibromide. Its IUPAC name is 1,2-dibromoethane. Here are some additional practice problems. Try to name molecules A, B, and C on your own before proceeding. Molecule A is 1,1-dichlorocyclopentane. Molecule B is correctly named 2,4-dibromopentane. In this molecule, you will get the same name whether you start counting from the left or the right. Molecule C is 7-bromohept-1e. You might see this written as 7-bromo-1-heptane. Using earlier IUPAC guidelines, the double bonds take priority over the halogen atom. So, carbon number 1 is at the far right. Practice is the key to learning organic nomenclature. Here are 2 problems to try on your own. What are the common and IUPAC names of these compounds? Vinyl bromide and allyl chloride are the common names of these molecules. What are their IUPAC names? The common name of compound A is secondary butyl bromide, and its IUPAC name is 2-bromobutane. The common name of compound B is neopentyl bromide, and its IUPAC name is 1-bromo-2,2-dimethylpropane. The common name of compound C is tertiary butyl bromide, and its IUPAC name is 2-bromo-2-methylpropane. The IUPAC name for vinyl bromide is bromoethane. No number is necessary for the possession of the bromine atom. Whichever carbon atom it is attached to must be the first carbon. The IUPAC name for the allyl chloride is 3-chloropropane. Because of the double bond, the leftmost carbon is at position number 1. Let's practice another important skill. That is, drawing structural formulae from names. It is best if you start with the end of the name, with the carbon backbone, and work forwards. Try them independently before checking the answers. The correct structural formulae are shown here for 2-bromo, 2-iodobutane, and 1-fluoro-2-methyl-cyclohexane. Remember that if there is more than one substituent, they are listed alphabetically. Halogens are more electronegative than carbon. Part 1. It is important to note that halogens are more electronegative than carbon. This means that halogen atoms have a greater tendency than carbon atoms to attract electron density to themselves. As a result, bonds between carbon and halogen atoms are polar in nature. In the carbon-halogen bond, the carbon atom has a partial positive charge, while the halogen atom has a partial negative charge. The atomic radii typically increases down a column. A trend that we observe here, from fluorine to iodine. Thus, the carbon-halogen bond length increases as we go from a carbon-fluorine bond to the carbon-iodine bond. As the bond length increases, the bond enthalpy decreases. This means that less energy is required to break the carbon-iodine bond as compared to the carbon-fluorine bond. Additionally, as the halogen atom becomes less electronegative, from fluorine to iodine, the carbon-halogen bond becomes less polar. Let's look at the methods to prepare alkyl halides. There are three main synthetic routes: from alcohols, from hydrocarbons, and from halogen exchange. We'll discuss each one in turn. Study a variety of reactions. Try to focus on the pattern of change in each type of reaction. Perhaps the best way to prepare alkyl halides is from alcohols, as alcohols are readily available. Essentially, turning an alcohol into an alkyl halides requires the substitution of a hydroxyl group of an alcohol by a halogen atom. One way to make alkyl halides from alcohol is through the reaction of alcohols with concentrated halogen acids, which have the general formula HX. Water is the other product of the reaction. In practice, this reaction is used primarily to prepare the alkyl chlorides and alkyl bromides. For primary and secondary alcohols, zinc chloride must be used as a catalyst in this reaction. Since tertiary alcohols are more reactive, no catalyst is needed. Tertiary alcohols react with concentrated hydrogen chloride within minutes at room temperature. To prepare alkyl bromides, boiling with hydrogen bromide is necessary. In general, with a given haloacid, tertiary alcohols are more reactive than secondary alcohols. Primary alcohols are the least reactive. This method is not suitable for the preparation of aryl halides. This is because the carbon-oxygen bond in phenols has a partial double bond character and hence is stronger and difficult to break. Practice is the key to remembering different types of reactions. So, there will be quite a few problems in this module. Try to answer the questions on your own before checking the answers. Here's the first problem. Write the chemical equation for the reaction that takes place between cyclohexanol and hydrogen bromide. Start by drawing out the structural formulae for the reactants. Then Substitute the hydroxyl group with the bromine atom to make bromine cyclohexane. Water is the other product of the reaction. Alkyl halides can also be prepared for reacting alcohols with phosphorus halides. In practice, phosphorus tribromide is the most common phosphorus halide used. A general equation for a reaction between an alcohol and a phosphorus trihalide is shown here. Note that the hydroxyl group is substituted with the halogen atom. The other product of the reaction, phosphorus acid, is water-soluble and can be removed by washing the alkyl halide with water. The variation of this same basic approach uses phosphorus pentachloride to convert an alcohol into an alkyl chloride. Sometimes these reactions are carried out by generating either phosphorus tribromide or phosphorus triiodide in situ. That is, making them right in the reaction missile. This is done by adding red phosphorus and either bromine or iodine to the reaction mixture. The substitution reaction is represented here with the reaction conditions written over the arrow. An alternative approach to make alkyl fluorides from alcohols is to use thionyl chloride, SOCl2, as a reagent. This reaction is used mainly to prepare primary and secondary alkyl chlorides. Thionyl chloride is preferred because the other products of the reaction, SO2 and HCl, are gases at room temperature and therefore can be easily separated from the alkyl chloride. Let's practice. What is the major monohalo product for the reaction shown here? You should recognize this type of reaction, a secondary alcohol reacting with thionyl chloride. One chlorine atom will replace the hydroxyl group to make 2-chloropropane. Sulfur dioxide and hydrogen chloride are the other products of the reaction. Now, write a balanced equation showing the formation of the monohalo product when ethanol reacts with phosphorus tribromide. Start by writing out the formulae for the reactants. You should recognize the pattern. An alcohol reacts with a phosphorus halide to make an alkyl halide. So, the monohalo product is bromoethane. Phosphorus acid is the other product. Be sure to balance the equation. Alkyl halides can also be prepared by free radical halogenation of alkenes. The general equation is shown here. You can think of it as the substitution of a hydrogen atom by a halogen atom. The free radical chlorination or bromination of alkanes gives a mixture of isomeric mono and polyhaloalkenes, which is difficult to separate as pure compounds. Hence, this method is not suitable for the laboratory preparation of pure haloalkanes. Let's apply our knowledge. 2-methylpropane shown here is reacted with chlorine. What are the two possible monochloro products for this reaction? Note that in 2-methylpropane, we have a tertiary hydrogen, as well as several equivalent primary hydrogens. Replacing the tertiary hydrogen produces 2-chloro-2-methylpropane, or tertiary butyl chloride. Replacing one of the primary hydrogen yields 1-chloro-2-methylpropane, or isobutyl chloride. Alkanes can be used as starting material to make alkyl halides. There are two main routes, the addition of hydrogen halides and the addition of halogens. Let's consider the addition of hydrogen halides to alkanes. The general reaction is shown here. When an alkane is reacted with the hydrogen halide, the hydrogen and halogen atoms attach at the location of the double bond. The resulting product has all single bonds. If the alkane is not symmetrical, then there are two possible products from the addition reaction. We can use Markovnikov's rule to predict which product will be more prevalent. According to Markovnikov's rule, the negative part of the addendum, that is, halogen in the present case, preferentially adds to the less hydrogenated doubly bonded carbon atom. Let's work through this problem together. 2-methylpropane reacts with hydrogen fluoride. What are the two main possible products of the reaction? Identify the major product. Start by drawing out the structure for 2-methylpropane. Note that it is not symmetric. One carbon atom in the double bond is bonded with two other carbon atoms, while the other carbon is bonded with two hydrogen atoms. Two products are possible as shown here. The top structure is the major product, according to Markovnikov's rule, as it put the added halogen on the carbon atom in the double bond attached to fewer hydrogen atoms. The lower structure is the minor product. If alkenes are reacted with halogens, vicinal dihalides are produced. Usually, these reactions use either chlorine or bromine. The general equation is shown here. Notice that halogen atoms attach to the carbon atoms in the double bond of the alkene, and so the halogen atoms bond to adjacent carbons. The addition reaction of bromine in CCl4 to alkene forms the basis for an experimental procedure to detect double bonds in molecules. Combine bromine in CCl4 and the unknown compound. If the reddish-brownish color bromine disappears, then this is good evidence for the presence of double bonds. No change in color would indicate the absence of double bonds. Try this problem on your own. Write the product of the reaction when cyclopentene is reacted with chlorine. Start by drawing the structural formula for cyclopentene. The chlorine atoms attach at the location of the double bond, resulting in the saturated compound with no multiple bonds. Although we didn't discuss the mechanism of this reaction, it turns out that the halogen atoms attach to the opposite faces of the double bond to give a trans structure. Halogens are more electronegative than carbon. Part 2. You may have noticed that most reactions discussed so far are not typically used to prepare alkyl iodides or alkyl fluorides. In many cases, this is because the reactions are thermodynamically inferable with iodine. Instead, halogen exchange is a more reliable route to prepare alkyl iodides. In the Finkelstein reaction, alkyl fluorides or alkyl bromides are reacted with sodium iodide in dry acetone. The resultant alkyl iodide is easily separated from the sodium halide salt that precipitates out. The general equation is shown here. Halogen exchange also provides a synthetic route to alkyl fluorides, which are difficult to make by the other methods discussed in this module. In the Schwarz reaction, an alkyl chloride or alkyl bromide is heated in the presence of a metallic fluoride, such as silver fluoride, mercurous fluoride, cobalt chloride, or antimony trifluoride. As shown in the general equation here, the fluoride ion is able to replace the other halogen atom, making an alkyl fluoride. Predict the major monohalo product when chloroethane is reacted with sodium iodide in dry acetone. After you write down the formulae for the reactants, you should be able to recognize the pattern for the Finkelstein reaction. The iodine in sodium iodide replaces the chlorine in chloroethane. Iodoethane and sodium chloride are formed. The sodium chloride precipitates in dry acetone, making it easy to isolate the iodoethane. To make aryl chlorides and aryl bromides, electrophilic substitution of arenes is used. These reactions require iron or iron 3 halides as Lewis acid catalysts. The general reaction is shown here. An aromatic ring such as benzene reacts with diatomic chlorine or bromine. A halogen atom replaces one of the hydrogen atoms to form an aryl halide and a hydrogen halide. Note that the reaction with iodine is reversible and requires the presence of an oxidizing agent such as nitric acid or iodic acid to oxidize the hydrogen iodide formed during the reaction. Chlorine is added to benzene in the presence of metallic iron. Write out a balanced equation showing the monofluoro product. Use the balanced equation. All the hydrogen atoms have been explicitly shown to clarify that one chlorine atom replaces one hydrogen atom on the benzene ring. Hydrogen chloride is the other product. The Sandmeyer reaction provides a synthetic route for the preparation of aryl chlorides from primary aryl amines. The general reaction is shown here. By writing the reaction conditions over the arrow, we can emphasize the changes in the functional groups. Note that an amine group is replaced with a chlorine. It's worth looking at the two steps in greater detail. In the first step of the Sandmeyer reaction, the primary aromatic amine, dissolved or suspended in a cold aqueous mineral acid, is treated with sodium nitrite to make a diazonium salt. In the second step, the diazonium salt is treated with copper 1 chloride to replace the diazonium group with a chlorine atom. Alternatively, to make an aryl iodide, the diazonium salt can be treated with potassium iodide. Test your knowledge with a problem. Predict the major monohalo product for these reactions. Note that the reactant in reaction A is a cycloalkane, but the reactant in reaction B contains an aromatic ring. Reaction A is an addition reaction. Based on Markovnikov's rule, the chlorine atom will attach at the same carbon to which methyl group is attached. Reaction B is a free radical halogenation reaction. A bromine atom replaces the secondary hydrogen atom in the alkyl substituent to the aryl ring. The hydrogens on the benzene ring will not be replaced under these conditions. In this module, we will be studying about the physical properties of haloalkanes and haloarenes. Pure alkyl halides are colorless. For example, methyl bromide or bromoethane is a colorless gas that can be used as a pesticide. However, this use is being phased out due to its toxicity. Historically, it was used as an industrial fire extinguishing agent. Methyl bromide is also known to be an ozone depleting chemical. The alkyl bromides and alkyl iodides may develop a color when exposed to light. For example, ethyl bromide turns yellow when exposed to light and air. Many volatile alkyl halides have a sweet smell, but this may not be noticeable unless the concentration is relatively high. Lower alkyl halides, including methyl chloride, methyl bromide, and ethyl chloride, as well as some chlorofluoromethanes, are gases at room temperature. Higher alkyl halides are liquids or solids. You have already studied that the carbon-halogen bond in halogen compounds is polar. Due to the greater polarity and higher molecular mass of haloalkanes as compared to the parent hydrocarbons, the dipole-dipole and van der Waals forces of attraction are stronger in these compounds. Hence, haloalkanes have considerably higher boiling points than those of the hydrocarbons of comparable molecular mass. For a given alkyl group, the boiling point increases with increasing atomic weight of the halogen. This is due to an increase in the magnitude of van der Waals forces of attraction with an increase in size and mass of the halogen atom. Thus, among the alkyl halides, alkyl iodides have the highest and alkyl fluorides have the lowest boiling points. For a given halogen, the boiling point increases with an increase in the number of carbon atoms in the chain. This is again due to the increase in the magnitude of van der Waals forces of attraction with an increase in the size of the carbon chain. The boiling points of isomeric haloalkanes decrease with an increase in branching. This is due to the fact that with an increase in branching, the molecule attains spherical shape with less surface area. This results in a decrease in the magnitude of van der Waals forces and hence the decrease in boiling point. Thus, among the isomeric butyl chlorides, the straight chain isomer, N-butyl chloride, has the highest, while tertiary butyl chloride has the lowest boiling point. The haloalkanes are only very slightly soluble in water. Why? For a haloalkane to dissolve in water, energy is required to break the attraction between the haloalkane molecules and the hydrogen bonds between the water molecules. As new attractions between the haloalkane and water aren't nearly as strong as the original hydrogen bonds in water, less energy is released during this process. Thus, haloalkanes are sparingly soluble in water. Haloalkanes do tend to dissolve in organic solvents. The intermolecular attractions that form between haloalkanes and the solvent molecules have similar strengths as the attractions being broken in the separate haloalkane and solvent molecules. Alkyl fluorides and alkyl chlorides are less dense than water. In a mixture with water, alkyl fluorides and alkyl chlorides would be the upper layer. Alkyl bromides and alkyl iodides are denser than water. In mixtures with water, alkyl bromides and alkyl iodides would separate into the lower layer. Increasing the number of halogen atoms increases the density of the compounds. Aryl halides are polar molecules due to the presence of polar carbon-halogen bond, but they are less polar than alkyl halides. Aryl halides have physical properties very similar to alkyl halides. We should make special note of the isomers of dihalobenzenes. If we compare the ortho, para, and meta-isomers of dichlorobenzene, we see that their boiling points are nearly the same. However, the para-isomers have higher melting points. The greater symmetry of para-isomers fits better into the crystal lattice, making the para-isomers melt at relatively high temperatures. Aryl halides are practically insoluble in water and are denser than water. Here is a problem for you. Arrange these compounds in increasing order of their boiling points. Let's start by drawing the structure for each compound. All the three structures contain one chlorine atom. Since the boiling point increases with an increase in the number of carbon atoms, we should expect one chlorobutane with its 4 carbon atoms to have the highest boiling point. The other two compounds have 3 carbon atoms each. But one chloropropane is a straight chain, while isopropyl chloride is branched. Branched molecules have lower boiling points, so isopropyl chloride should have the lowest boiling point. One chloropropane is in the middle. In this module, we will be studying about the chemical properties of alkyl halides. Haloalkanes undergo three types of reactions. They are nucleophilic substitution reactions, elimination reactions, and reaction with metals. Let us first study about the nucleophilic substitution reactions. Before you learn about the nucleophilic substitution reactions, get to know what a nucleophile is. The word nucleophile means nucleus seeking. Essentially, a nucleophile has an unshared pair of electrons, and it can use these electrons to make a covalent bond. Nucleophiles can be thought of as Lewis bases or electron pair donors. Nucleophiles may be anions or neutral molecules. In nucleophilic substitution reactions, A nucleophile, or a Lewis base, substitutes for a halogen atom in an alkyl halide. Here is the general form of the reaction. The halogen is referred to as the leaving group because it leads the alkyl halide when the nucleophile reacts. Since the substitution reaction is initiated by a nucleophile, it is called the nucleophilic substitution reaction. Common nucleophiles include the hydroxide ion and water, both of which react with alkyl halides to make alcohols. Ammonia and substituted amines are used to convert alkyl halides into amines. Note the lone pairs on each formula. Sodium or potassium salts of alkoxides can be used to make ethers from alkyl halides. Sodium or potassium salts of carboxylates can be used to make esters from alkyl halides. Sodium iodide can be used to make alkyl iodides from alkyl halides. Lithium aluminium hydride can be used to convert alkyl halides into hydrocarbons. Some nucleophiles can be described as ambident nucleophiles. These contain two nucleophilic centers and so can link to the alkyl halide in two different ways. For example, the cyanide ion can link through the carbon atom to make alkyl cyanides. If a cyanide ion links through the nitrogen, alkyl isocyanides will form. The nitride ion is another example of an ambident nucleophile. If it links through the nitrogen, a nitroalkene will form. It can also link through the oxygen to make alkyl nitrides. Depending upon the mechanism or the reaction conditions, nucleophilic substitution reactions can be classified as SN1 or SN2 reactions. The S is for substitution and the N is for nucleophilic. Since these reactions are initiated by the nucleophile, the number gives information on the reaction kinetics. 2 for bimolecular and 1 for unimolecular. Let's start with the SN2 reaction. The reaction between 2-iodobutane and hydroxide ion to yield 2-butanol is an example of an SN2 reaction. This reaction follows second-order kinetics, meaning that the reaction rate depends on the concentration of both the nucleophile and the alkyl halide. As the slow step or the rate-determining step involves two molecules, the mechanism is termed as bimolecular. This reaction occurs in a single step and does not involve any intermediate. Take note of the three-dimensional arrangement of the atoms around the carbon in the alkyl halide. The solid wedge is used to show the bonds coming out of the plane of the screen. The dashed lines show bonds going down the plane of the screen, while the straight lines represent the bonds in the plane of the screen. In the SN2 mechanism, the nucleophile attacks from the back of the molecule, on the opposite side from the halogen atom. The leaving group in this reaction, the leaving group leaves simultaneously. This is described as a concerted mechanism, that is, a one-step mechanism, because the new bond between the nucleophile and the carbon atom forms at the same time as that of the carbon-halogen bond breaks, as shown in the pentacoordinate transition state. Since the carbon atom is bonded to 5 atoms, the transition state is unstable and hence cannot be isolated, as the bond between the nucleophile and the carbon atom forms. The bond between the carbon and the leaving group weakens. The nucleophile essentially pushes the leaving group of the carbon atom. There is only one type of product in an SN2 reaction. If you compare the alkyl halide reactant and the substituted product, you can see that they have opposite stereochemistry. This switch is called an inversion of configuration. Let's apply our knowledge of nucleophilic substitution reactions to a couple of problems. What happens when 2-bromo-octane is treated with aqueous potassium hydroxide? Let us start by writing out the reactants. The hydroxide ion is the nucleophile. See how it approaches the carbon atom from behind. Notice the inversion of configuration as the hydroxide ion pushes the bromide ion out to make 2-octanol. What happens when methyl chloride is treated with potassium cyanide? KCl is ionic, so it generates a cyanide ion, which attacks the carbon in the methyl cyanide. In principle, the cyanide is ambivalent and could attack from either end. However, the CC bond is more stable than the CN bond, so methyl cyanide is the primary product. If we wanted to make methyl isocyanide as the primary product, we should have used silver cyanide as the nucleophile. Since silver cyanide has significant covalent character, linking through the nitrogen atom predominates. As you have seen, the reaction involves the approach of the nucleophile to the carbon bearing the leaving group. Hence, the presence of bulky groups on or near the carbon atom will hinder the approaching nucleophile. Thus, among the alkyl halides, methyl halides, due to the presence of only 3 small hydrogen atoms, are the most reactive in SN2 reactions. Tertiary alkyl halides, on the other hand, due to the presence of bulky groups, are the least reactive in SN2 reactions. Thus, the order of reactivity of alkyl halides towards SN2 reactions is as shown here. Non-total leaving groups react equally well. In general, among the halogens, fluorides are the poorest leaving groups, and iodides are the best leaving groups. In these pairs of halogen compounds, which would undergo an SN reaction faster, let's start by drawing out the structures. For the first pair, 1-bromohexane is a primary alkyl halide, and cyclohexylbromide is the secondary alkyl halide. We expect 1-bromohexane then to be more reactive and react more quickly. For the second pair, both structures are secondary haloalkanes. However, iodine has a weaker bond to carbon than chlorine. Alkyl iodides are much more reactive than alkyl chlorides. Now, it's time to turn our reaction to the other mechanism called the SN1 reaction mechanism. The reaction between 3-bromo-3-methylhexane and hydroxide ion to yield 3-methyl-3-hexanol can be taken as an example of an SN1 reaction. The reaction shows first-order kinetics as the reaction rate depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. The reaction occurs in two steps. In step 1, the leaving group departs, resulting in the formation of the carbocation. This step is slow and reversible. In step 2, the nucleophile attacks the carbocation, forming a covalent bond. The greater the possibility of the formation of a carbocation by an alkyl halide, the higher are the chances for the reaction to proceed via the SN1 mechanism. Further, the greater the stability of carbocation, the greater will be its ease of formation from an alkyl halide, and the faster will be the rate of reaction. Thus, due to the greater stability of tertiary carbocation, tertiary alkyl halides readily undergo SN1 reactions. Allylic and benzylic halides also show high reactivity towards the SN1 reaction. This is because the allylic and benzylic carbocation bond gets stabilized through resonance, as shown here. SN1 reactions are usually carried out on polar protic solvents such as water, alcohols, and acetic acid. The proton from the solvent molecules solvate the halide ion as it leads in the first step of the mechanism. In the SN1 mechanism, there are two directions from which the nucleophile can attack the carbocation. Two different products can be formed from the SN1 mechanism. Compare the product that is formed when the nucleophile approaches from the left compared to when the nucleophile approaches from the right. They have the same formula, but different arrangements in space. These two products are mirror images of each other. They are not superimposable. Even if we rotate the right-hand molecule around the bond between the black and blue atoms, it still doesn't match the left-hand molecule. We call these as enantiomers. In the SN1 mechanism, both enantiomers are equally likely to form. This is called racemization, and such 50-50 mixtures are called racemic mixtures. You will learn more about terms such as enantiomers and racemic mixtures, as well as about the stereochemical aspects of the nucleophilic substitution reactions in the next module.
अभी कौन सा चैप्टर चल रहा है हमारा अभी अपने लिए बच्चा कर रहा है एप्लीकेशन डेवलपमेंट स्मार्ट स्ट्रक्चर ये तरफ शुरू कर रहा है ये क्लास सकते हैं जैसे उसका भी तो उसका भी हम सेकंड स्टार्ट करते हैं ये तो फर्स्ट सेकंड थर्ड तो हो गया डिटरमिनेंट मैट्रिक्स ये होगा तो फिर तो सिक्स्थ तो करिए उसके ये मीनिंग होगी इस पर हर चक्कर अलग है जो जुड़े हुए हैं वो आपको बीच में यहां पर प्रैक्टिस तो आप कितने समझ तो आ रहा आपको पता तो है ना मेरे को पता है कि मेरा आपका किस टाइप के क्वेश्चन आते हैं सब मेरे को सीरियस तो फिर आपको बताऊंगा कौन से क्वेश्चन कैसे आए ठीक है वो आप में आप कब आते हैं ना इनको तो अलग अलग तरीके हैं वो बोलेगा बता देना मतलब बता देना बात हुई ऐसे करे तो करे करे हमने मैक्सिमम 16 साल दे दी है तो फिर बाबू से इकट्ठे करेंगे जैसे आपके वैसे पूरे साल के वाले 18 जो अपने हमने थोड़ा सर तो आप उसी का नहीं है बस मैं कोई डिटेल ना हो रही है जैसे मुझे आपका बस ठीक है सुबह शाम जैसे छुट्टी वाले दिन रहने वाले कोई बात नहीं मैं डिसाइड कर लो घर पे ठीक